All right, people, it is the beginning of a new chapter, which means you should have been doing a lot of reading. All right. This chapter is very, very difficult. At least I think so. So let's kind of be a little focused. All right. Now, energy. Energy is a topic that we've kind of been like referencing to. We haven't really taken the time to understand it. So let's kind of talk about what we have referenced before. What we talked about before has been a type of energy called kinetic energy. When we talked about temperature, last chapter we figured out that temperature is a direct relationship to the kinetic energy of something. So temperature is a measure of the energy of motion, how many particles are moving, or how fast are they moving, and that's what determined kinetic energy. Now there is another type of energy called potential energy, and potential energy is the energy that is stored. It is stored energy, and it can be stored in one of two ways. It can be stored because of what the material is. For example, let's say you have gasoline. It has the potential to release a lot of energy, right? If I get a lighter and just go kaboom, then it has the potential to release. It has a lot of stored energy. Or think of a boulder high up on the hills. It has the potential to roll down the hill and cause some damage, right? So that is the potential energy. Now, the total energy in something is made out of the potential energy plus the kinetic energy. All the energy is one of those two things. So say you're studying the boulder on the hill, well, it's made out of the potential energy and the kinetic energy. So if one of these goes up, the other one will go down so that the energy can stay the same. Because energy staying the same is a fundamental property. It's a law of thermodynamics. It tells us that the energy in the universe is constant. It stays the same. So the energy just changes. It's never destroyed. It just changes form. So it can change into kinetic and change into potential. It can change into thermal heat as a waste byproduct, right? Now, let's think of this object, right? This object is high up in the hill, so it has a lot of potential energy. Now, let's say it begins to roll down the hill. Well, now it's moving. So it loses that potential energy because now it's not as high as it once was. And it starts to move, so the kinetic energy goes up. All right, and then let's say eventually this hits this ball and it brings this ball upwards. All right, so what would that look like? Well, now it's over here. So what has happened? Well, the ball A has dropped down in potential energy. The potential energy went down. It used up a lot of that kinetic energy while going down. And while that kinetic energy, it lost that kinetic energy in some form, right? So the change in energy occurred. So a way it could have lost some of that kinetic energy would have been, well, as it's rolling down the hills, it's rubbing up against things. It's rubbing up against the dirt or against the grass, or it's hitting a tree, or it's hitting rocks, or just the friction from rolling it can cause some energy to leave. So the energy of A can change. The energy of A can change, and it changes dependent on two variables, and two variables that are very, very important for us to talk about today. That change in energy is going to be in one of two forms. It's going to change in the form of heat, or it's going to change in the form of work. All right, so the heat could have been coming off of the object as it rolls, and the work, it could have been hitting things along the way. So sometimes there's less heat that's released, but more work is done. But the change in energy is always the same, regardless of whether a lot of heat was lost or a lot of work was done. Either way, the change in energy is going to be the same always. This is a very important concept of a state function. It's a property of energy. A state function is a property that does not depend on the pathway. All right, so it's a property of an object that doesn't change depending on how you get there. So let's think of a property of, let me move this, get away, move you over here. Let's think of like the property of a mountain. Okay, so a mountain, let's say this one is, it's a very short mountain, it's 4 feet tall. No. Yeah, it's 4 feet tall. We'll keep it at 4 feet tall. It's a giant mountain. And you're 0.000000004 feet or whatever. You're super tiny. So the height of this mountain is always going to be the same. That property of the mountain is going to be the same. All right, that is a state property. Let's say this person, this super tiny thing, had to climb up this mountain. So it takes a path, it goes on its own little hike, and it climbs up, and it takes it a few days, and eventually reaches the top. So the change in height, the change in elevation was a state function because it didn't make a difference of the path it took. He still got to the same height, but the distance traveled is not a state function. Does that make sense? Hopefully it does. And if not, I'll try to make another video explaining state functions only. But energy is a state function, as in it doesn't matter how it got there. It doesn't matter how it got there. The change in energy is going to be the same. So just as it applies to a ball rolling down and going up a hill, it can apply to the energy in chemical reactions, and that is what's more important to us. All right, so we're going to talk about this because this energy in chemical reactions is a very, very important topic. It's what led to the Industrial Revolution. So understanding energy was a very, very important thing in history. All right, now let's talk about some chemical reactions. Right, this chemical reaction, there's two types of chemical reactions. There are reactions that produce heat, that release heat, and then there are reactions that absorb heat. So there are endothermic reactions, those absorb heat from the surroundings, and exothermic reactions where energy is released as a byproduct and it comes off as heat. So the gasoline, for example, you burn gasoline, releases a lot of heat. That releases a lot of energy. That's an exothermic process. Now, let's see how the change in energy. We said that potential energy is chemical energy, right? It's energy that it can release. And let's see how the reactants and products look like for a exothermic reaction. So remember that the energy of the whole thing, remember the energy is excuse me. So let's think about this in terms of energy. This has a certain amount of energy, and then these have a certain amount of energy, but some of it was released. So these right here are going to have less energy than those because they lost some. Does that make sense? So how do we draw this visually? Let me move these. So these have higher energy, the reactants, than the products. And it doesn't matter where we put them. Let's just put them off to the side. Okay, we just put them off to the side over here. So, hello, please. Patience, Mr. Sanchez. Paciencia. Don't. Okie dokie. Hello. Uh-oh. Oh no, come on, man. I'm like halfway through the video. Alright. Why is it doing this to me? Okay. Yes. Oh, thank goodness. I was about to cry. Did you see the life leave my eyes? Alright. But I don't know how to edit, so all right. But anyways, the potential energy has changed from this system, from this chemical reaction, the thing we're studying, the system has changed, right? Originally, these two reactants had more energy, but as the reaction happened, their energy went down. But that leftover energy, we said that the energy can be destroyed. This energy leaves in the form of heat. So heat can be our change in potential energy, right? Because if our potential energy leaves, it can be heat. And this is what we call an exothermic process, okay? And in a way of visualizing this, a very common way, because you will have like multiple choice questions on these things, like I hate explaining that, but the reactants are always higher energy than the products in an exothermic reaction. They had more energy, the reaction happened, so now it ended with at a lower energy, and the leftover energy, this PE, came off in the form of heat. So let's see, we had that's Q. We just explained Q as being a change in potential energy. Now we have to explain what work is. Oh, but before that, let me show you an endothermic reaction. All right, getting ahead of myself. So an endothermic reaction is the same way. Let's draw the potential energy, and this is lower potential energy and higher potential energy. So in this case, this is an endothermic reaction. So these two have less energy than this one, okay? Because you had to add more so the energy can be the same on both sides. So what that does, it actually absorbs energy from the surroundings. It takes energy away. And it is actually this is actually a reaction that gets really cold. All right, so the potential energy in the beginning is lower. It's lower than at the end. So the change in energy here, in this case, I forgot to explain the math. We will explain the math, but the change in energy here is going to be positive. And on the other one, it was negative, and I'll explain why, but it all has to do with the direction of the way heat flows. All right, so maybe make note that delta P in an endothermic reaction, the heat in an endothermic reaction has a positive sign. All right, and the heat in an exothermic reaction has a negative sign. It all has to do with direction, nothing else. All right, but let's check this out. Here's a little summary of what that looks like. So a system is whatever you are studying. Say you're studying a simple chemical reaction. Well, try to isolate that chemical reaction as much as possible. That's your system. Everything else is your surrounding. So there are two types of systems when it comes to energy flow. All right, so if energy leaves, that's a negative symbol. That's an exothermic process. So exothermic. So if you ever touch something hot, is because it's been releasing the heat. Its heat is leaving. All right, so exothermic. If energy goes in, it pulls energy out from its surroundings. So the surroundings get cold. All right, and that's an endothermic process. So knowing the direction of the way heat flows or the way energy flows is very, very important. When heat leaves, it's negative. When heat comes in, it's positive. Just in going in, positive, going out is negative. It's not more, it's not less. Get the math ideas. What you've been taught in math is different than what you've been taught in physics. Physicists see negatives and positives as directions. It has nothing to do with more or less. All right, it's all about direction. All right, now we talked about energy. We talked about the change in energy being equal to the heat, which we just described, plus W. Now, W is work. Remember the definition of energy: the capacity to do work or produce heat, or I forget the definition, whatever. All right, but the point is, let's talk about work. Work is a force applied over a distance. What does that mean? Work is basically like pushing something or lifting something. It's moving one object from one position to another position. Does that make sense? Hopefully it does. All right. So let's check this out. Work, the mathematical definition is the pressure times the change in volume. But there's a lot of equations for work, because work is just basically pushing one thing, applying a force over a distance. Applying a force over a distance. Now, a force, we haven't really been talking about forces except for one time when we talked about gases. When we talked about pressure, we said that the pressure of a container is due to the particles hitting the container. So the pressure is depending on how many particles hit the container or how much force they apply in that area. All right, so imagine a piston. Imagine a piston, and its initial conditions had this volume, right? It's staying perfectly still. But if these gas particles push up inside the container and they push it till it comes up here, they have applied a pressure and they made the container change a certain volume. So they applied a force over a distance, and that was our work. So that took energy, right? Remember, energy is equal to heat heat plus work. And this is a concept of the engine, right? It's basically how an engine works. There's a chemical reaction, releases heat, or it produces work. It can push things. So a combustion from gasoline doesn't just release heat, but you can use it to push something. And if you use it to push some pistons back and forth, they keep doing that, to then turning into some rotational energy, then you got yourself a little engine, and you got yourself a little car. All right, so this delta H helps us find our delta V. Your book does a whole bunch of math explaining it, showing it, but the main idea is to know that work is due to the change in volume in an area times the pressure, the number of particles that were like crashing into it, right? Now the next thing we're going to do is we're going to talk about some practice problems relating to all this, but hopefully that gave you a little bit of an understanding. Let's do a little quick review. Remember that your total energy is equal to your potential energy plus your kinetic energy. And remember, your change in energy is equal to your heat and your work. And the signs of these, the signs of Q and W, do not mean more, do not mean less. If you ever see a negative or a positive, it has to do with direction. If heat comes in, it is positive. If heat leaves, it is negative. If you do work, right? If the chemical reaction can push something, so if it can push a piston, or if it can expand something, it can move things out of its way, if it can produce work, then W is positive. But if you have to compress down into the system, if you have to do work onto the system, like compressing the gas and decreasing the volume, our work is going to be negative. If I can find a good simulation of a diesel engine, I'll show how pushing stuff in can. Never mind. We'll talk about that later. But these are the main ideas from energy, okay? And it's gonna get a little bit more complicated. So if you have any questions, please ask, okay?